Hello everyone and welcome back to today's lecture on energy efficient buildings. My name is Mohammad Ehtisham and our focus today will be on lecture 35, compliance requirement from module number 11, building codes and standards. The future of building energy code implementation is poised to significantly enhance energy efficiency and sustainability across the built environment by developing enhanced compliance systems, integrating smart technologies and adapting to climate change and harmonizing standards globally. We can ensure that building energy codes remain a vital tool in addressing our energy, economic and environmental changes. Previously, we have already discussed overview of building energy codes, its importance and purpose, international, national and local energy codes, compliance pathways and requirements and future prospects. The overview of building energy codes provides a comprehensive introduction to the importance, development, adoption, compliance and enforcement of these codes, highlighting their crucial role in helping us tackle our energy, economic and environmental challenges. The outline of today's lecture will be compliance requirements for energy efficient buildings, key requirements for achieving energy efficiency, strategies for compliance with energy codes, and role of energy modeling and simulation. Energy performance compliance is a critical aspect of modern building design and construction aimed at reducing energy consumption and promoting sustainability. It ensures that buildings are designed and constructed to meet specific energy efficiency standards, minimizing their environmental impact and reducing operational cost. This presentation delves into the intricacies of the ECBC code compliance framework, focusing on key concepts such as the Energy Performance Index or EPI and EPI ratio. We will explore various compliance approaches including mandatory requirements, prescriptive methods and the whole building performance method. Additionally, we'll discuss essential documentation and tools used to demonstrate compliance, providing a comprehensive understanding of energy performance standards in building design. Energy performance compliance is a multifaceted process that involves a collaborative effort between architects, engineers, contractors and building owners. It requires careful planning, design consideration and implementation of sustainable strategies to achieve optimal energy efficiency. This presentation will provide a comprehensive overview of the ECBC compliance framework, guiding you through the key aspects of ensuring energy efficient and sustainable building. Energy performance compliance, ECBC compliance framework. The ECBC code establishes a comprehensive framework for evaluating and ensuring energy efficiency in buildings. It sets minimum energy performance standards for various building components and systems, including envelope design, HVAC systems, lighting and appliances. The ECBC aims to reduce energy consumption, minimize greenhouse gas emissions and promote sustainable building practices. Energy Performance Index or EPI. The EPI is a crucial metric that quantifies a building energy efficiency. It is calculated as the annual energy consumption per square meter of the building total built-up area, excluding unconditioned basements. This metric helps assess a building's energy performance relative to a standard baseline and provides a valuable tool for comparing different designs and technologies. EPI ratio. The EPI ratio compares the proposed building's EPI to that of a standard building. A ratio of less than equal to 1 indicates compliance with energy performance standards, demonstrating that the proposed building is at least as efficient as the standard. This ratio is essential for demonstrating compliance with the ECBC and ensuring that buildings meet the specified energy efficiency goal. Mandatory requirements. All buildings must meet specific mandatory requirements outlined in sections 4.2, 5.2, 6.2 and 7.2 of the ECBC code. These encompass various aspects of building systems and building design, including minimum insulation levels for wall and roofs, energy efficient lighting fixtures, and performance standards for the HVAC systems. These requirements establish a baseline level of energy efficiency that must be achieved by all the buildings to comply with the code. Understanding the Energy Performance Index or EPI. The Energy Performance Index EPI is the fundamental metric in assessing building energy efficiency. It is defined as the annual energy consumption per square meter of the building. The EPI provides a standardized measure of energy use intensity, allowing for comparisons between buildings of different size and types. The EPI help assess a building energy performance relative to a standard baseline and provides a valuable tool for comparing different design and technologies. The EPI ratio is a critical component in determining compliance with the energy performance standard. It is calculated as the EPI of the proposed building divided by the EPI of a standard building. A ratio of less than equal to 1 indicates compliance with energy performance standards, demonstrating that the proposed building is at least as efficient as the standard. This ratio is essential for demonstrating compliance with the ECBC and ensuring that building meets the specified energy efficiency goal. To achieve compliance, the EPI ratio must be greater than or less than equal to 1, indicating the proposed building is at least as energy efficient as the standard building. It's important to note that EPI values should be rounded off according to IS 1960 standards to ensure consistency in calculations and comparison. The EPI and EPI ratio serve as key indicators for a building energy performance. They provide a quantitative basis for evaluating compliance with energy codes and standards. By comparing the proposed building energy consumption to that of a standard reference building, these metrics offer a clear and objective measure of energy efficiency, guiding designers and engineers in creating more sustainable structures. The EPI is a crucial tool for measuring and tracking the energy performance of buildings over time. By monitoring EPI values, building owners and operators can identify areas for improvement and implement strategies to enhance energy efficiency. This data can also be used to benchmark performance against industry standards and demonstrate commitment to sustainability goals. Furthermore, the EPI plays a crucial role in promoting transparency and accountability in the building sector. It allows for consistent comparison across different buildings, facilitating informed decision making and encouraging the adoption of best practices. By fostering a culture of transparency, the EPI helps drive innovation and advancement in building energy efficiency. Compliance approaches and methods. Mandatory requirements. All buildings must meet mandatory compliance requirements regardless of the chosen compliance method. This requirement covers essential aspects of building design and systems to ensure a baseline level of energy efficiency. These mandatory requirements typically addresses key areas like insulation levels, glazing specification, ventilation systems, and lighting efficiency standards. This ensures that all buildings, regardless of their specific design approach, meet a minimum threshold of energy performance. Prescriptive method. The prescriptive method involves meeting prescribed values for envelope components, comfort systems, and lighting. It includes sub-methods like the building envelope trade-off method and total system efficiency method, offering flexibility in achieving compliance while adhering to specific prescriptive requirements. The prescriptive method provides clear guidelines and specific requirements for each building element, making it relatively straightforward to understand and implement. It's particularly beneficial for simpler projects where the design and construction process can be readily adapted to meet the predefined standards. Next is whole building performance method. The whole building performance method or WBP method allows for a more holistic approach to compliance. Under this method, a building can achieve compliance if its proposed design energy use is less than that of the standard design, even without meeting specific prescriptive requirements. This approach offers greater design flexibility while still ensuring overall energy efficiency. The WBP method provides a more dynamic and adaptable approach to energy performance compliance. It encourages innovative design solutions that may not adhere to traditional prescriptive standards but still demonstrate effective energy performance. The EPI ratio and WBP method. When using the WBP method, the EPI ratio is calculated by comparing the proposed building energy performance to that of a standard building. Compliance is achieved if the resulting EPI ratio is greater than or equal to 1, demonstrating that the proposed design is at least as energy efficient as the standard. This approach allows for a more comprehensive evaluation of the building energy performance, considering its overall energy use and efficiency, rather than relying solely on individual component specification. Compliance documentation and tools, construction drawings, detailed architectural and engineering drawings that illustrate the building design include envelope specification, HVAC system, lighting layouts, and renewable energy installation. These drawings provide a comprehensive visual representation of the building energy related features, facilitating a thorough understanding of the design and its potential impact on energy performance. Specification: comprehensive technical specification for all the building system and components relevant to energy performance, including materials, equipment, and installation requirements. These specifications provide detailed information on the selection and implementation of the energy efficient technologies and materials, ensuring that the building construction and the operation meet the prescribed standards. Compliance tool: approved software tools such as the online BEP EMIS software or whole building energy simulation programs for demonstrating compliance through accurate modeling and calculation. These tools enable architects and engineers to conduct simulations and analyze the building energy consumption under various scenarios, providing insights into its energy efficiency and potential areas for improvement. Additional administrative and supplemental information are required to verify compliance include energy calculations, equipment schedules, and commissioning reports. These verification documents, serve as evidence that the building energy performance meets the established criteria, demonstrating compliance with the regulatory requirements and promoting energy efficiency throughout the building's life cycle. Introduction to the whole building performance method. The whole building performance method or WBP method offers an alternative approach to energy conservation in building design as outlined in the Energy Conservation Building Code. This method provides flexibility for architects and engineers to optimize energy efficiency across various building systems while meeting the mandatory requirements. Unlike the prescriptive method, the WBP method allows for innovative solutions and trade-off between different building components, making it applicable to all building types covered by the ECBC. The WBP method encourages a holistic approach to building design, considering the interaction of various building systems and their impact on energy performance. This method allows for a more customized approach, tailoring solutions to specific building needs and local climatic conditions. By evaluating the building energy performance of the entire building, and the WBP method promotes a comprehensive understanding of energy consumption patterns and potential areas for optimization. To achieve compliance using the WBP method, building must demonstrate an energy performance index EPI ratio of 1 or less, indicating that the proposed building design performs at least as well as a standard reference building. The EPI ratio is calculated by comparing the building estimated energy use to that of reference building, considering factors such as building size, climatic conditions, and occupancy. A lower EPI ratio indicates better energy efficiency. This approach encourages holistic thinking in building design and promotes the integration of energy efficient technologies and strategies. By focusing on overall energy performance rather than prescriptive requirements, the WBP method facilitates the implementation of innovative solutions such as renewable energy system, advanced building materials, and smart building technologies. Calculating annual energy use and trade-off. The whole building performance method offers flexibility in building design by allowing some trade-off between different building systems, while still ensuring the overall energy performance of the building meets and or exceed the standard. To use the WBP method, you need to calculate the building's annual energy use and compare it to the standard reference building. The following steps outline the process for calculating the building energy use and conducting a trade-off analysis. Step number 1: annual energy use calculation. Calculate the building energy annual use in kilowatt hours per year per unit area. This includes all energy sources with non-electric sources converted to kWh at a rate of 0.75 kWh per megajoule. This calculation considers factors such as building size, climatic condition, and occupancy. A lower EPI ratio indicates better energy efficiency. Step 2: proposed design simulation. Use approved simulation software to model The proposed building design incorporating all the energy related features and system. This include factors such as building orientation, window glazing, insulation levels, HVAC systems, lighting fixtures and renewable energy sources. The simulation software will then calculate the building energy use based on these inputs. Step number 3, standard design simulation. Create a parallel simulation of the standard reference building which meets all the prescriptive ECBC requirements. This simulation will serve as a benchmark for comparison against the proposed design. Step number 4, trade-off analysis. Compare the annual energy use of the proposed and the standard design. This analysis allows for trade-off between different building systems while ensuring that the overall energy performance of the building meets or exceeds the standards. This means that you can make changes to the building design such as adding more insulation or using more effective HVAC system and then compare the energy use of the revised design to the standard design. This allows you to optimize the building energy performance while still meeting the requirements of the ECBC. The WBP methods allow for significant flexibility in design, permitting trade-off between different building systems. However, it's important to note that this method can be applied to building permits covering less than the whole building, provided that the design parameters not covered by the permit remain identical for both the proposed and standard design. This approach ensures a fair comparison while allowing for partial renovation or additions to existing structures. Documentation and compliance too. Documentation requirements. To demonstrate compliance with the WBP method, project team must provide comprehensive documentation. This includes a detailed summary of analysis reports showcasing the energy used for both the proposed and standard design. The documentation should also contain a thorough description of the project details, energy related features and how the design meet all the mandatory requirements outlined in section 4 through 7 of the ECBC code. The documentation should be clear, concise and easily understood by reviewers, providing a comprehensive overview of the project's energy performance and compliance with the WBP method. Compliance tool. Simulation programs play a crucial role in WBP method. These tools must provide detailed input and output reports, clearly explaining modeling assumptions and any error messages encountered during the simulation process. It's essential to choose software that is approved for use with the ECBC and capable of accurately modeling the proposed building energy systems and features. Additionally, the software should be user-friendly and allow for easy data entry and analysis, enabling project teams to effectively conduct simulations and generate accurate results. To verify the compliance, project teams must submit building plans and site plans alongside the energy simulation results. These documents allow reviewers to cross-reference the model design with the actual building specification, ensuring that all energy-related features are accurately represented in the simulation and that the building as designed will meet the required energy performance standards. The verification process aims to ensure a robust and thorough assessment of the project's energy performance, confirming that the proposed design meets or exceeds the established energy efficiency standards. Ensuring compliance in building design simulation. Simulation consistency. Utilizing the same simulation program for both the proposed and standard designs to ensure the comparable results. This consistency is crucial for accurate energy performance assessment and compliance calculation. For example, if you are using Energy Plus for the proposed design, make sure to use Energy Plus for the standard design as well. This consistency is necessary to eliminate any discrepancies that may arise from using different simulation engines. Weather data uniformity. Apply identical weather data sets to both design models. This approach eliminates variables that could skew the comparison between the proposed and standard design, providing a level playing field for evaluation. Make sure to use the same weather data files. This ensures thereby eliminating any potential bias introduced by different weather data sets. Operational assumptions. Maintain consistent building operation assumption across both models. This ensures occupancy patterns, equipment usage, and other operational parameters that significantly impact energy consumption. Use the same schedules, equipment operating hours, and other relevant operational data for both the proposed and standard design. This consistency is crucial for accurately assessing the energy performance differences between the two designs. Energy simulation model requirements. Developing accurate and compliant energy simulation model is crucial for evaluating the energy performance of building design. We'll discuss the essential requirements for creating models that meet code standards and provide reliable data for informed decision making. Table 9.1 of the ECBC code serves as a critical framework for developing energy simulation models for both the standard and proposed designs of buildings. It outlines specific requirements for various components, ensuring that energy efficiency measures are accurately represented and compliance with energy codes is achieved. The table is essential for maintaining consistency and accuracy in energy modeling. First parameter, design model. The design model for the proposed design must align with the design documents accurately representing fenestration, opaque envelope types and areas, as well as interior lighting power, HVAC system types, controls and sizes. This ensures that the energy model reflects the actual design intentions and specification. For the standard design, the model is developed by modifying the proposed design according to the specification mentioned in the table. Unless specified otherwise, all building systems and equipment should be modeled identically in both the standard and proposed design. This approach ensures that any energy efficiency measures can be directly compared against a baseline model that adheres to mandatory and prescriptive requirements. Second one, space use classification. Space use classification is crucial for determining the operational characteristics and energy requirements of different building zones. The proposed design must clarify and classify building types or space types in accordance with section 2.5 of the ECBC code, allowing for more accurate modeling of mixed use facilities. The standard design follows the same space use classification as the proposed design, ensuring consistency in how different spaces are treated in the energy model. Third one is schedule. Operational schedules including hourly variation in occupancy, lighting power, equipment power and HVAC operation are essential for demonstrating compliance with energy codes. These schedules must be suitable for the building or space type and model as per section 9.6 of the code. Both the standard and proposed design must have identical temperature and humidity schedules and set points, with exceptions allowed for non-standard efficiency measures subject to approval. Fourth one is building envelope. The building envelope in the proposed design must be modeled according to the architectural drawings or as installed for existing buildings. Exceptions are permitted for elements covering less than 5% of the total area of that assembly type. The standard design must have identical conditioned floor area, exterior dimension and orientation as the proposed design, with specific exceptions noted in the table. This includes orientation consideration where performance is averaged across multiple simulations with different building orientation. Fifth one is lighting. Lighting power in the proposed design is determined based on the existing systems or design specification. It includes all lighting system components such as lamp or ballast. Minimum lighting control as per the ECBC requirement must be modeled in the proposed case. In the standard design, interior lighting power is determined using the same categorization procedure as the proposed design, with power set to maximum allowed by the ECBC. Lighting control must comply with ECBC standards. Sixth one is HVAC thermal zones. HVAC zones in the proposed design must be modeled based on design drawings, with each zone treated as a separate thermal block. Identifying zone may be combined for simplicity. If HVAC zones are not defined, they should be based on similar occupancy, internal loads and set points. The standard design follows the same zoning approach as the proposed design, ensuring consistency in thermal modeling. The HVAC system type and related performance parameters in the proposed design should reflect actual system types and efficiencies. If no system is specified, assumptions are made to ensure consistency with the standard design. The standard design uses a similar approach but with system types and efficiency aligned with code requirements, ensuring a fair baseline for energy performance comparison. Number 8 is service hot water. The service hot water system type and related performance parameters in the proposed design should reflect actual system types and efficiency. If no system is specified, No surface hot water heating is modeled. The standard design should include a solar water system capable for meeting 20% of the hot water demand for residential facilities, hotels and hospitals. Ninth one, miscellaneous load. Receptacle, motor and process load should be modeled and estimated based on the modeling type and space type category. These loads must be included in simulation for both the standard and proposed design. 10th one, modeling's limitation to the simulation program. If the simulation program cannot model a component or system in a proposed design method, such as ignoring the component, substituting a thermodynamically similar component, or using the HVAC system of standard design may be used, subject to approval. The component must be modeled identically for both designs. To summarize, Table 9.1 provides a structured approach to developing energy simulation models for building design. By ensuring consistency and adherence to energy code, it facilitates accurate comparison between proposed and standard design. This is essential for achieving energy efficiency and compliance with building regulations, ultimately contributing to sustainable building practices. Standard design adherence. Ensure all the standard design model incorporates all mandatory and prescriptive requirements for ECBC compliance. This serves as a baseline for comparing the energy performance of the proposed design. This means that the standard design model should represent the building as it would be built if it were to meet the minimum code requirements without any additional energy saving features. This provides a benchmark for evaluating the energy performance improvements achieved by the proposed design. Proposed design accuracy. Model the proposed building design to accurately reflect the actual building specification, including any innovative or energy efficient features that deviate from standard practices. This includes modeling all building components, materials and systems such as HVAC systems, lighting system and envelope insulation with high fidelity. The model should accurately represent the performance of any proposed energy saving technologies such as solar panels, geothermal heat pumps or high efficiency lighting fixtures. Followed by documentation. Maintain comprehensive documentation of all modeling assumptions, inputs and methodologies used in both the proposed and standard design simulation for transparency and verification purposes. This documentation should include detailed description of all modeling parameters, data sources and assumptions made during model development. It should also include a clear explanation of any deviations from the standard modeling procedures and any limitations or uncertainties associated with the model. This comprehensive documentation facilitates review and verification by stakeholders, ensuring the accuracy and reliability of the simulation results. HVAC system and energy compliance. Ensuring compliance with ECBC code is paramount for sustainable building design. They detail the specific compliance level of HVAC system in relation to the ECBC. The ECBC outlines specific criteria for HVAC system, which are critical components in achieving energy efficiency in buildings. The requirements are categorized into 3 compliance levels: ECBC, ECBC Plus and Super ECBC. The Energy Performance Index or EPI ratio is used to measure the energy efficiency of HVAC system. This ratio compares the actual energy consumption of a system to the energy consumption of a reference system. Lower EPI ratio indicates greater energy efficiency. The table also presents the EPI ratio requirements for various climatic zones and compliance levels. For instance, in a hot dry climate, an HVAC system achieving ECBC compliance must have an EPI ratio of 1 or less, while the ECBC Plus system requires an EPI ratio of 0.91 or less. By adhering to these compliance levels, building designers can ensure that HVAC systems contribute to overall system efficiency and meet the requirements for sustainable construction. These regulations encourage the use of energy efficient technologies and design strategies, leading to a reduction in building energy consumption and a positive impact on the environment. In conclusion, ECBC Energy Simulation Model provides a structured approach to designing energy simulation models for building design. By ensuring consistency and adherence to energy code, it facilitates accurate comparison between proposed and standard design. This is essential for achieving energy efficiency and compliance with building regulations, ultimately contributing to sustainable building practices. In the upcoming lecture, we will explore the case studies in code compliance with emphasis on examples of energy efficient building projects, deployed compliance strategies and challenges faced, and key lessons learned from the successful code compliance projects. Thank you for your attention.